Hi, I'm Tyler Leitz.
I'm Timothy Zhao.
And I'm Soham Kulkarni, and together we're working on Wikigraph, which is an effort to visualize Wikipedia and the relationship between articles. When we were thinking about this, we wanted to have a good way of thinking about how articles are related with each other and the best way to present them in a format that is like comprehensive. So we started with getting the data. So for this, we used the SNAP dataset from Stanford, and we tried to get the relationship between two articles using breadth first search and Dijkstra's algorithm. So we visualized the dataset using a four-space drawing, and we also highlighted paths using the shortest breadth first search result.
So like he said, we used the Stanford SNAP dataset of English Wikipedia in 2013. And this dataset, as you can see here, came as a list of edges with node IDs. And initially, there were over 4 million nodes and 100 million edges, which was way too much for us to process. So to remove the edges, we scanned through the Stanford SNAP dataset, and we had a lower and upper bound for our node ID. And if we met an edge with either node outside of that lower and upper bound, we wouldn't include it in our trim dataset. So with our processing, when we reduced the number of nodes to 1,000, we had approximately 1 to 2,000 edges. And when reducing the dataset to 10,000 nodes, we had approximately 100,000 edges.
So to find the relationship between two articles, we tried two different approaches. The first one was a simple breadth first search where we found the shortest path on an unweighted graph between two nodes. And we tried a different and more unique approach by using Dijkstra's algorithm and converting our graph to a weighted graph using the in degree heuristic. So articles in our data set are related to each other using hyperlinks. So when an article has a reference to another article, we form an edge between those two. Well, we saw that we sometimes did not see a meaningful relationship between two articles because of really popular nodes such as calendar years or units of measurement. So to overcome this issue, we weighted every edge based on the in degree of the node that they are pointing to. So using this heuristic, we were able to filter out or normalize nodes which were referenced a lot.
For actually visualizing our graph, we used a force-space method. And in a force-space method, nodes are treated as particles and attractive and repulsive forces are added to them. A physical simulation is then run and the forces are applied each iteration of the simulation until final positions for each of the particles are calculated. And then each of the particles are drawn onto the screen with lines connecting them being edges. Right. So for the actual physics behind our force-based drawing algorithm, we're using a similar approach to uiuc's algorithm. So pretty much for nodes that are adjacent to each other, they have an attractive force that's similar to an elastic force. So from the instance Hooke's law, but in this case, we're taking the log of the distance between them and then multiplying it by some constant. And then that's the attractive force between them. And then we are also applying Coulombic forces to nodes to repel them from each other so that nodes won't be clustered together. So for that, we're assigning a charge to each node, which is just its in degree. And then we're dividing by the distance squared between two nodes and multiplying by a constant. And that's the repulsion between two given nodes. So basically there's two kinds of forces at work where nodes in general will repel each other, but nodes that are linked, so that are similar in a sense will attract each other. So clusters in the graph will form where nodes that are adjacent to each other will be close to each other in the drawing as well. Right. So for the code structure of force-based drawing, we have a simulation singleton which controls the physics logic for our code. Each node is put into a particle object which has some basic attributes like position, velocity, acceleration, mass, etc. And then forces themselves are modeled using higher order functions. So a force is just type def to a function that returns a 2D vector and takes in two particles. So you can think of it like as a formula for a force, for instance. And then rendering is done by a renderer singleton, which will take in a graph and actually run the simulation and then draw the output to a PNG. All right, so the time complexity for a force-based drawing, if you do a naive time complexity, we're going to iterate through all the edges basically, and then apply an attractive force between the two endpoints of the edge. And so that takes O of E time. And then if we want to do it naively, for any two nodes in the graph, we apply a repulsive force to them, as stated earlier, and that's going to take O of V squared, two loops over the entire set of nodes. So in total, we have O of E plus V squared per duration. In general, it's recommended to run O of V iterations from the resources we find online. So if we do that, then our overall time complexity ends up being O of VE plus V cubed, which isn't very good. So we want to do better than that. So basically, the way we're going to reduce the runtime is by making two observations. If the graph is sparse, so there's not a lot of edges, then the runtime is going to be dominated by calculating repulsive forces. And then also that for nodes that are far away, the repulsive force between them is going to be very strong because since the forces are coulombic, it falls off rapidly as the distance increases because it's inverse squared relationship. So we can simplify this to only applying repulsive forces to nodes that are close together. So each iteration, we're going to build a KD tree in O of V log V. And then assuming that the tree is balanced, we can query for nearby points in approximately O of square root of V. Then calculating all the repulsive forces, we'll take around O of V to the 3 over 2. Then the per iteration time complexity now gets down to O of E plus V to the 3 over 2. So for 1K nodes and 1K iterations with a radius of 10, so only nodes that are within 10 units of each other exhibit repulsive forces towards each other, this ends up being about a 2x speedup.
So here is one example of a force-based drawing that we created. 1,000 nodes that are math related, and it's the shortest path from SymPy to graph theory is highlighted on here. And as you can see, nodes such as graph theory, who are very related to other nodes, will be closer to the center with a lot of other nodes around them, and they'll be larger because that's their size is scaled by their mass. And nodes such as SymPy, who have very few edges, will be drawn smaller and can be seen farther away from the center of the drawing.
So for our final conclusion, based on our shortest path algorithms and our force-based drawings, we first noticed that Wikipedia is a very densely linked graph, and there are a lot of edges between nodes. We found the issue of having articles which were highly referenced that were not giving us meaningful relationships, and we were able to solve this by using the integrate heuristic that produced more meaningful relationships between two nodes. And finally, we realized that on a large data set like ours, optimizing time complexity is worth the effort. For example, using KD trees improved our runtime by a factor of 2 on a data set of 1,000 nodes.
With more time, what we would look to improve would firstly be the user experience, because right now the user, when interfacing with the graph, has to find out the node ID of all of the pages that they want to work with. So by having some sort of lookup so that the user can just enter the page instead of having to look up the ID themselves would be a great improvement on that front. And also we would look into animation on the force-based drawing, because that would look pretty cool. And if the simulation is like stagnating, and we could fine tune the parameters to like make the force-based drawing better. And then finally, we would experiment with different weights for edges, because with our data set, there wasn't much that we could look into with the edges. But if, for example, we could mine or find a data set that tells us how many words into a page a hyperlink is, then we could have other meaningful ways to relate web pages to each other.